Hello, good morning, and welcome to our lectures on sonographic principles and instrumentation. And I'm sure the lectures we have done so far has helped in shaping the ongoing development of the device using AI and nanotech technology. So today we're going to look at pulse wave ultrasound parameters. Like we've discussed, we've looked at the components that makes up the machine and how the machine works. But in this, we're going to be particular and we'll make progress from there. So ultrasound transducer produce two waves. That is the pulse wave ultrasound, and there's a continuous wave ultrasound. So we'll look at the continuous wave ultrasound first, because it's not the major thing in the current diagnostic machines, but it's one of those things that we use in Doppler studies. But we'll look at it quickly, then go back to the main thing, which is pulse wave ultrasound. So continuous wave ultrasound cannot produce image. A transducer working with the continuous wave mode always has two crystals. One group of crystals for transmitting ultrasound waves and another group of crystals for echo reception. Now the transmitted waves has uniform amplitude and frequency. And in this case, the duty factor is 1 because there's a continuous production of sound and a continuous reception of sound. Now we'll discuss about duty factor in other when we speak about pulse wave, but just to mention here in case I don't come back, is the duty factor is 1 because it's always transmitting. Yeah. So continuous wave ultrasound is actually less common, and we use that in Doppler echocardiography to obtain continuous wave Doppler information where there is very high range of flow velocity beyond the range of pulse wave Doppler. So now pulse wave ultrasound is much common in use. All the machines, most of the machines you see around operate on pulse wave. So all diagnostic grayscale ultrasound imaging operates on pulse wave, color Doppler, and pulse wave Doppler, except for continuous wave that does not operate on pulse wave because it's continuous. So for real-time scanning and any other type of ultrasound image display, like A mode, B mode, M mode, the system must be operating in a pulse wave ultrasound mode in order to construct an image on the display. So with pulse wave ultrasound, an ultrasound pulse is not continuously generated like in the continuous wave. Instead, the transducer operates in a pulse mode and uses the same crystal to transmit ultrasound wave and to receive echoes. So pulse transducer transmits ultrasound in a series of short pulses. Remember when we were talking about the pulsar in the first lecture? I told you how that it releases bursts of voltages. So that creates the pulsatile nature of the sound wave that is produced. So that's pulse wave ultrasound. So between successive pulses, the transducer is in reception mode, receiving or listening to the echo between every transmission. So that is an ultrasound pulse is transmitted. When it's transmitted, is actually the on time for that machine, or the talking time, and then there is a pause. It stops to transmit. It transmits and stop before the next transmission, before the next pulse is emitted. So that time it's on is called the on time or talking time. So during the pulse time, the transducer is receiving reflection from tissues, which we call the off time or the listening time. So the crystals emit and receive signal in an alternative fashion, with 1% of the time allotted to production of sound. That is, 1% of the time is the machine is on time, and 99% of the time is off time, as listening time. So in other words, the machine listens, the transducer listens more than it speaks. So in pulse wave ultrasound, each pulse consists of a collection of 2 to 3 individual wave cycles. So you may want to consider that like the cars of a train. So the 2 to 3 individual wave cycle will form each cars. Then the pulse, which is the train, moves as one, containing the 2 to 3. So we have car 1, car 2, car 3 that will contain wave cycle 1, wave cycle 3, wave cycle 3, wave cycle 3, all in a train. That's one pulse with wave cycles in each of them. So in pulse wave ultrasound, a pulse must have a beginning and have an end, otherwise it will be continuous. So that's why I try to depict it as the cars of a train. There needs to be a starting point and there's an ending point. So there are 5 additional parameters which we'll look at in pulse wave ultrasound to describe pulse wave ultrasound, which will be the PRF, the PRP, the PD, SPL, and DF. So PRF is actually a pulse repetitive frequency. PRP is pulse repetitive period. PD is pulse duration. SPL is spatial pulse length. DF is duty factor. So we're going to look at each and every one of them and see how these parameters interplay to produce for us the pulse that we'll be listening for echoes to produce an image. So we'll start with the first one, which is pulse repetitive frequency. Now this is the number of ultrasound pulses that is transmitted in a second. Yeah, the rate a pulse transducer is electrically activated to produce and transmit an ultrasound pulse wave is known as PRF. So the rate at which that transducer is triggered electrically to produce and transmit ultrasound pulse is the PRF. All ultrasound images are created using the series of pulses. And the PRF is a very important concept, and it's analogous to frequency, but it's not frequency. Yeah, but as we go on, you understand what I'm trying to say. So it typically range from 1,000 to 10,000 frequency. The unit for PRF is hertz, and is usually determined by sound source and can be adjusted by the sonographer or the operator. The PRF is determined by the pulsar. Remember the pulsar in our first lecture? The PRF is limited by depth, that is imaging depth. Since an ultrasound system must wait for all the echoes to return before transmitting another pulse, the deeper the depths of the field, the lower the maximum PRF must be set. So if you want more penetration, you have to reduce your PRF. The lower the PRF, the deeper the penetration, and vice versa. So PRF is inversely proportional to the depth of field, just like I said. So PRF is a key factor in many ultrasound process, such as the frame rate and the Doppler. So do not confuse it with frequency, like I've said before. The two are unrelated, but it's analogous to one another. Yeah. So the equation, PRF is equals to inverse PRP, is an introduction of pulse repetitive period and how it relates. We'll get to that. But in this equation, PRF, we already know what it is, pulse repetitive frequency. PRP is pulse repetitive period. And PRP is measured in meter per second. PRF is pulse per meter per second. So it is reciprocal to PRP and imaging depths. That's PRF is reciprocal to PRP and the depths. Remember what we said about depths? So here, when depths increase, PRP increase. In other words, the period for pulse repetition increases. So PRP, increase in PRP means inverse proportionality for PRF. In other words, PRF will decrease. Increased depths means decrease PRF. Like we've mentioned, it's very important to take note, because as we develop this, we'll be doing a lot of adjustments to see what gives us, at what level of PRF and PRP will give us the best image quality. So what are the limitations to this PRF? PRF is limited by the time it takes for echoes to return to the transducer. The longer the distance, that is the depths, yeah, the longer the echo arrival time. Thus, the PRF is inversely related to the display depths, just like I just mentioned in the other slide. PRF is inversely related to display depths. So as the display depths increase, the maximum PRF decreases, and vice versa. I keep repeating these things because it is very important for development and quality of image. And image is everything. The end user understands the image, not how the image come about. So if you mess up with these ideas, these principles, you mess up with what the end user can appreciate. Now let's look at PRP, pulse repetitive period, and it's defined as the time from the start of one pulse to the start of the next pulse. So remember our chart, we have pulse, pulse, pulse. Yeah? So the start of one pulse to the start of the other is PRP. So it includes both the on time and the off time. It's analogous to period, but it's not period. It's measured in milliseconds and is determined by the sound source. The sonologist or the operator can change the PRP using whatever knob that is provided. Or nowadays machines, there's been automation, so sometimes the machine just do that when you change your frequency or probe. So PRP is reciprocal to PRF. They have inverse relationship. So when the operator adjusts the depth of view, the operator actually alters the receiving time. Yeah. So every time you zoom, you try to zoom or bring the image closer, you're actually adjusting the depths. So what you are doing, you're adjusting PRP. So you're adjusting the listening time of your probe. So the depth of view, that is the penetration, is directly related to PRP and inversely related to PRF. So in this equation, you see increase in depth means increase in PRP. increase in PRP means decrease in PRF. So the equation is an inverse proportionality of PRF. So PRP is composed of two intervals. Yeah, a PD, that's pulse duration, which is the time during which the transducer is generating ultrasound. It is also called the on time. And reception time or off time is the time during which the sound transmission is off and the system is listening for echoes. So the reception time varies with imaging depths, like we said. But in current ultrasound system, the PRF automatically adjusts when the operator selects depths. So these are the two periods. The time where the machine speaks, that is the first period. The second period is the time when the machine listens. So PRP composed of these two. PD, which is pulse duration, is the time it takes for a pulse to occur. It is the time from the start of a pulse to the end of that pulse. Yeah, it's only the time that the pulse is on. That is the transmitting of the pulse. That is what PD measures. PD is very short. Each ultrasound pulse consists of few cycles of ultrasound. So we have pulse 1 with 3 cycles, pulse 2 with 3 cycles, pulse 3 with 3 cycles. Yeah. Typically there are 2 to 3 cycles sound in each pulse. But I would advise we keep it at 3 because ultrasound machine these days is at 3 cycles. So I advise we put our device at 3 cycles per pulse. The unit for pulse duration is microsecond or seconds and is determined by the sound source. The pulse wave duration equation here shows number by time, where the number means number of cycles per pulse, how many cycles are in a pulse. Remember, I said we should just peg it at 3 times t. T is a period. So since period is a reciprocal of frequency, the formula can be written as this: PD number of cycles over frequency, where T is period, frequency is measured in megahertz, and PD is the duration in microsecond. So if the pulse is produced by, for example, let's do this quick calculation in our mind. If the pulse is produced by 5 megahertz transducer, the pulse duration will be what? Using the formula PD N over F. N is number of cycles, right? I would say we are pegging it at 3 cycles. Yeah, and we have the frequency 5 megahertz. So what would that be? 3 divided by 5 will give us 0.6 microseconds. So PD is directly proportional to period, and PD is directly proportional to the number of cycles per pulse. So PD is inversely proportional to frequency. So an increase in period or number of cycles per pulse will increase PD. A decrease in either will shorten PD as pulse duration. Look at spatial pulse length, SPL. That is the length or the distance that a pulse occupies. Start of a pulse to the end of that pulse. So it's the distance it occupies, yeah? Often is simply stated as pulse length, which I'm used to. And it's analogous to wavelength, but it's not wavelength, it's analogous to it. The unit is in millimeter or centimeter, and it can range from 0.1 to 1 millimeter. Source can be determined by medium, as it is determined in the wavelength, and the operator cannot change this because it's medium determined. So spatial pulse length decreases when the wavelength decreases or the frequency is increased. There are a few cycles in the pulse. Let's see this equation here. SPL is n lambda, and since lambda is velocity over frequency, SPL can basically be number of cycles by velocity over frequency. Yeah, number of cycles in the pulse. So for soft tissue, we already know the velocity for soft tissue, which we are using 1.54 millimeter microseconds. So for soft tissue, you can do the calculation, number of cycles and the frequency. So remember, number of cycles, we'll peg it at 3 cycles. We already know the soft tissue constant, and let's pick maybe frequency of a probe for 5 megahertz. Do the maths and you'll be able to appreciate what the spatial length will be. So the pulse duration decrease, the pulse duration describes a pulse temporarily in relation with time. The SPL describes the pulse spatially, that is lengthwise, yeah, the length of the pulse. And SPL in a pulse is very short, typically around 1 mm. So SPL has clinical importance and is a primary factor which determines the axial resolution of image and thereby image quality. So if we're talking about the length of that pulse, yeah, so it means that if we reduce the length, we are going to be affecting the axial resolution. How axial resolution is distinguishing 2 points that stand side by side. So if you reduce the length, you may narrow it to just one or a portion of one and full of the other one. You may not appreciate the whole image to know that these are 2 points. But if you leave it at a reasonable size, you can now delineate between this point and that point. That's the idea. That's what it does for us clinically. So good axial resolution requires short pulse, and typically is 1 mm. Axial resolution will refer to how close 2 reflectors can be, what I was trying to explain, to how close they can be to one another and still be distinguishable as separate reflectors along the beam path. So axial resolution, which will depict as R subscript A, is equal to SPL over 2. So as the length of the pulse is decreased, that is spatial length decrease, the axial resolution improves. And when the resolution improves, of course, you know, the quality, image quality improves and is desirable. Also, what's the relationship? SPL, spatial pulse length, is directly proportional to wavelength. Spatial pulse length is directly proportional to the number of cycles in a pulse. Spatial pulse length is inversely proportional to frequency. So as the frequency is increased from 5 megahertz to 7 megahertz, the spatial pulse length will decrease due to a decrease in wavelength. So axial resolution will improve. So you have better image quality in higher frequency because the spatial pulse length is decreased in higher frequency. Now, duty factor. I said we're going to come back to duty factor. This is the percentage or the fraction of time that your ultrasound machine is producing a pulse or transmitting sound. It's also called duty cycle, yeah, and it is a fraction of time that sounds actually is emitted. So, duty at what time? What's the actual time that there was a transmission? That is what we are measuring for duty factor. But a pulse wave is not always producing, yeah. So the unit for duty factor is expressed as percentage and is basically unitless. And it is determined by sound source only, and the operator can change it. In some machines you have the DF, where you adjust these things. So duty factor is, we have a pulse duration over PRP times 1000. The 1000 is used to convert milliseconds to microseconds for consistency with the numerator, because PD, pulse duration, is measured in micro in millimeter. So since PRP is reciprocal of PRF, so we can now write this equation. Duty factor is pulse duration times PRF over 1000. What is the relationship? DF, as duty factor, will increase when pulse duration or PRF are increased. Excuse me. So when the PRP increases, the duty factor decreases. That's to say, increased depths, increased duty factor. Not duty factor, increase pulse duration, yeah? Increased depths, increase PRF. Increase PRP, decrease duty factor. So the duty factor, I need you to take note of this. Duty factor has no unit, and duty factor is a ratio and can only be expressed as decimal fraction or percentage. For pulse ultrasound, the duty factor must be less than 1, because it's not always emitting sound. It's a pulse, start and stop, on and off, yeah? So it has to be less than 1, and usually in pulse ultrasound, a typical duty factor will range from 0.001 to 0.01, and always is less than 1, like I've said, but it's usually greater than 0.0001. So if duty factor is 1 or 100%, the ultrasound machine is always producing a pulse, and that will be continuous wave. It's no longer pulse wave ultrasound. So in continuous wave ultrasound, the duty factor is 100%, 1. The sound is always on, yeah? And if the duty factor is 0, there's actually no pulse, and the ultrasound system is off. Duty factor is inversely proportional to PRP. Duty factor is proportional to PRF directly. Duty factor is important in relation to study of intensity. So you look at this table, pulse wave. We look at pulse wave parameters and what can be changed. These things I've said them before. Just take a look at them and you appreciate what I've said. Thank you for joining on this class. It's more practical than it's theoretical, so we're going back to the lab to test out these things we just said, apply all the parameters and see the best fit that will fit our device using this technology. Thank you for joining, and I will see you in the next class where we'll deal with more issues.